back. Today, we're going to be talking about convolutional neural networks. We'll actually also do a little bit of wrap-up on unstructured SVM topics. Part of the reason for this is for homework 3, we're actually going to have you implementing semantic segmentation, which is a problem where at the pixel level you're actually trying to figure out in an image what category a particular pixel belongs to, whether it's grass or sky or a dog or a cat or a tree. And so to do that, we'll have you build a structured SVM learning algorithm, but we'll have it backed by features that are coming from a convolutional neural network. And so this is kind of a useful tool, specifically when we move to this problem space of doing structured prediction for images or for video, as the case may be. Okay, so that's going to be homework 3, and we think that we'll have it out tomorrow, and then I think that we're going to aim to kind of keep the deadline around Monday. It might be like kind of plus or minus a day. We're actually kind of working on adjusting this assignment just so that we're going to try to make the CNN part of it really clear, what we want you to do, maybe even to the extent of sort of giving you some code for that, and then allow you to kind of focus on the actual structured SVM part. And 2 other details. So for the midterm exams, we won't be releasing a PDF copy of your exam to you. This is partly because, unfortunately, I've experienced lots of cases where my exams end up on the internet, on websites where you can purchase them and their solutions. So just by keeping them on paper, this seems to not happen. So anyway, it's really obnoxious for us, it's really obnoxious for you guys, but we're going to do it anyway. And so the earliest possible exam viewing we would have would be sometime today if we can get our act together in the next hour or so. Otherwise, we'll have them throughout this week. As well, mid-semester grades are due at like 4 p.m. today, and so I believe I've actually already released the letter grade portion of them, but no explanation whatsoever for where that letter grade came from. So I'll be releasing the actual explanation of different numbers that were compiled together to get your mid-semester grade. And so partly this is also just a chance for you to be double-checking my work. So I'll send you out a summary describing each of the different components, and so I generally just ask that you kind of take a look and make sure that we didn't make any mistakes. So great. Okay, so to talk a little bit more about structured SVMs, I wanted to wrap up just with a discussion of some actual results. So here we're going to be working with some results from when structured SVM was kind of first coming out, and so these are all linear models where we have some weight vector W and some features of the given input X and whatever variables you're trying to predict Y, and so what we're doing here is classification just by maximizing that score of W transpose F. And then learning is going to be via structured SVM. So here, an important detail is that the original name for structured SVM was Max Margin Markov Network, which is abbreviated as M3N. But in this class, I think its analogy to structured perceptron is so strong that I think it's actually easier to just kind of think of it in the name that we've been using. And but this name shows up in the literature and as well on these slides. So here we can look at like a couple different models, say for handwriting recognition. This is a slide that I had pulled up before, but now I actually want to focus a little bit differently on the actual M3N results. So here, the first baseline model is just taking each character for an optical character recognition task and independently predicting what letter it is. And over here, this is a linear chain CRF over those characters, where it's using a similar linear model for the actual factors that touch the image. So there's some features extracted from that little image. But then it adds in these little edges between subsequent variables so that you can have the model learning something about which characters are likely to follow other characters. Like an R is very likely to follow a B, for example, but it's very unlikely to follow a Z in English. Okay, so the third bar here shown is the same model as for the CRF, but trained not by maximizing likelihood, but by minimizing the structured hinge loss that we learned how to do last time with structured SVM. And so what's interesting here is that just by making that change to the objective function, we actually see this pretty dramatic improvement in test error on this task. So the only change was, the model is exactly the same between the CRF bar and that M3N bar. The only thing that changed is in the CRF bar, the objective function was likelihood of the data, and with the M3N bar, it was structured hinge loss. Okay, so there's this other detail that I'm not going to talk about, partly because it's not as in wide use today, but just as you can, do kernels with SVMs, you can also do kernels with structured SVMs. Though I tend to think that, the way that we're going to be using them with neural nets is probably a more modern and useful way of going about it. So this task is interesting because it actually relies on approximate inference, which we haven't yet discussed, and so what it's the actual task is trying to do is classify each page as either a faculty page, a course page, a student page, a project page, or other. And so this collection of web pages was collected from 4 CS department websites, probably CMU, Stanford, Berkeley, MIT, something like that. And so there are 1,300 individual pages and 3,500 links between those pages. And so the train test split is actually by university. So 3 of them were for training and the 4th was for testing. And so now you can imagine a graphical model where each page has a variable. And there are edges between pairs of variables for which one page links to another page. So this would result in some complicated looking graph, and it would probably have cycles in it. And so there's lots of different ways that you could do inference for this sort of problem. In this particular case, they used what's called loopy belief propagation, which is exactly the same as the belief propagation algorithm that you learned, except that it won't actually converge, or there's no guarantee that it would converge to true marginals or a true map assignment for this graph. So you send messages just as you normally would. And so here, again, we see that you can still train with structured SVM, though now you're no longer getting necessarily the true map assignment, but maybe some approximation to it. Okay, so named entity recognition is just a tagging task. I'm not going to go into details here. It's sort of similar to what you were doing on homework 1, where you were trying to label actual natural language, where here the actual goal is to identify persons, organizations, and locations, or a fourth category, miscellaneous. And so you would try to identify that, the UN is an organization, and Richard Butler is a person, and Baghdad is a location. And here again, using sort of what's so interesting about this is just that, using the same model, the structured SVM is outperforming the CRF. Huh. Huh? What? Wow. Okay. So I think that's fascinating. So these slides look entirely normal on a Mac. So my guess is that we're having some sort of yet another Windows issue. I still haven't actually resolved the font issues, and I'm guessing this is sort of related. So let's hope that I successfully posted slides for today. I didn't actually update the schedule. No. Okay, well, we'll do this. We'll do this in handwriting. So, I guess so. But come on, that would be so obnoxious. Okay, well. Right. We don't need all of these slides, but I really actually do want you to see 2 of them. All right, this is the slide that I care about. The other ones don't even really. Okay, so let's start with this horizontal slide. And I think mental rotation is probably just generally good for your brains, So we'll just leave this one as it is. And so here, what you can see is that the Markov max margin Markov network is getting 93% accuracy, whereas it's sort of beating out some baselines. Okay, so what I care about is that what we're going to be doing here is trying to label different pixels as, so this is just sort of a segmentation task in 3 dimensions, where the label is either the ground, a building, a tree, or a shrub. And these are all now sideways buildings, just to give the classifier an extra challenge. And the data is actually collected by this robot that can move around in a real 3-dimensional environment and collect these 3D point clouds. And then we're trying to actually label these 3D point clouds as being different types of objects, right? Okay, so how might one do this? Well, one way that you could do this is by building what's called an associative Markov network. And you could think of an associative Markov network as really just another name for a pairwise Markov random field. Okay? The reason that it gets a special name is because we're going to train it as if it were a structured SVM model. So essentially, associative Markov network, you can just think of as structured SVM plus pairwise MRF. And there's one more detail, which is that the actual pairwise MRF has a lattice structure. Okay. So those three ingredients, we're going to give the name associative Markov network. And this particular three-dimensional variant of this model, I think, is a little bit obscure. I haven't actually seen a lot of work done in this space. I think, though it's a little bit outside my area, the much more common model that we see all over the place is the two-dimensional version of this, which would apply when you're trying to do, say, segmentation on an image. So that's the variant that you'll look at. But here, what we have is this sort of three-dimensional lattice of points, and adjacent points have an edge between them. And that edge has some potential function attached to it. Okay. So this gives us both point potential functions and edge potential functions. And the way that they happened to define this model was with a log linear formulation. So they actually had features of these different points. Okay. And so by training this pairwise MRF with structured SVM, they're able to train a model that then makes a single prediction for a most probable assignment to that model. So the thing that you should be thinking about contrasting this with is the solution that we came up with in homework 2. So in homework 2, we said we're going to do some maximum likelihood like learning objective, and then for every variable, we're going to independently return the most probable assignment to that variable according to that variable's marginal probability. So what that means is that when you return the point value for one variable, it's not actually looking at what value you returned for its neighbor variables. Here, because we're going to return a single most probable assignment, right? We're going to return some y hat that is the argmax over y hats of p of y hat given x. We're going to return some assignment to these variables that is internally cohesive. So the slides that aren't showing here were basically just sort of a visual depiction of that internal cohesiveness. So I'll debug the slides, and I think actually the slides that I was trying to post on the website should correctly include this. Okay, so before we jump to CNNs, I want to make sort of two important notes about structured SVM. So the first of these is we can actually think through what it would look like to do structured SVM with neural potential functions. So here, the idea would be that we're going to let the scoring function, s of w of x and y, be defined by a hybrid of a neural net plus a conditional random field. And so an example of this would be if we define the scoring function to be by some factor graph. Okay. So this would be a product over a bunch of potential functions, psi alpha, where each one takes y alpha and x. And crucially, you'll notice this blank space here, where I've written nothing. So whenever we write, this product over the potential function, I guess maybe the blank space, I should say, is really up against it, right? So there is no term here that corresponds to the partition function, or the inverse partition function. So here, we're not actually going to be thinking about what the partition function is. We will, however, say that these potentials are defined by some neural net. So here, this is some neural network that takes in both y alpha and x and returns a table of values that it represents our factor. Okay, and this could be, for example, an LSTM or a CNN or some other neural network that you like. Okay. So pictorially, we could think of this as sort of two steps where we take our vector x and we feed it into a CNN, and that CNN outputs some representation of our vector x, call it z. And then separately, what we have going on is some graphical model, which consists of variables like y1, y2, y3, y4, and there's some factors connecting these together. And we could say that to actually compute those factors, we're going to take the output of the CNN and use it to compute these factors. So now recall that for structured SVM, the unconstrained objective that we had come up with last time looked something like this. So we said we're going to have some L of W that we're trying to minimize, which is a sum from I equals 1 to n of a bunch of little terms Li of W. Now I'm going to write this a little bit differently than what we saw before. Where, I think we might need a whole line just for Li of W here. So where Li of W is defined as, say, 1 over 2n, right, times the L2 norm of W squared. Okay, so what did I just do? Well, before we had this L2 norm of W outside of the summation over our training examples. I just multiplied it by 1 over n so that I could push it inside that sum. And then we had plus some constant c times a max of 0 and now our sort of more interesting structured hinge loss term, which was a max over all y hats in the set yxi. So here's where the I is coming in. This is going to be our ith training example of SW xi y hat plus the loss of yi with y hat. And now we close these brackets for the maximization and subtract off the score for xi and yi. Okay. So what do we have here? Well, the first bit is we have this weight term. This is like an L2 regularizer. And if you were actually to go implement this, you would find that you can actually not include this in your objective function, but just use what's usually called weight decay in your optimizer. So if you have an optimizer like Atom or something like it, stochastic gradient descent, you can turn on weight decay. And what that will do is just update your parameters at every time step so that they're gradually decreasing, as they should if they were L2 regularized. Okay. Now, so this was the update to W that came from that L2 regularizer term that we had in our structured or stochastic subgradient structured SVM algorithm last time. Okay, so now the next thing to notice is that this, where we have a maximization over y hat, this is essentially fixed for a given theta and I. Right? If you know what theta is, and you know what I is, then you, or sorry, not theta, W. So our parameters here are W. So if you know what our parameters W are, you can figure out which y hat maximizes this by running loss augmented map inference, or loss augmented inference. Okay, and then this max, well, this one is subdifferentiable. And what that means for us is that it's sort of supported by our backprop implementation. So you can include this max in your actual loss function definition. Right? We know how to get a subgradient of it. This one, we don't really back propagate through, but rather it's fixed for a given W and I, and so we can work with it directly. And then the last detail is that essentially what we're doing here is we're saying that this whole part is defining a loss using the score of the current sort of winner of loss augmented inference. And the score of the ground truth. Right, so this is the score of the ground truth, and this thing is the score of the sort of winner of loss augmented inference. Okay, so we've talked a lot about loss augmented inference. I wanted to actually have us look at an actual example of loss augmented inference. So this, we're going to say, is a new section. So our example here is going to be derived for a silly-looking graphical model consisting of 3 variables, where the first 2 are connected by a factor psi12, and the third variable, y3, is actually disconnected. It just has its own potential function, psi3. Okay. And so you could suppose, that for each of these yt values, they can take on different values, including red, blue, and purple. And the first thing that we're going to assume is that our probability factorizes according to this graphical model. So that would mean the log probability of y1 y2, and y3 is given by the log of psi1, 2 of y1, y2 plus the log of psi3 of y3 minus the log of the partition function z. Okay, so that's our first assumption. And then our second assumption is that our loss function, which is some L of the vector y star, which is all three y1, y2, y3 variables, and the vector that we're predicting. And so this y star is the ground truth here. And we're going to assume that it consists of two terms, L of 1, 2, and that's going to look at y1 star and y2 star, as well as y1 hat and y2 hat. And a second term, L of 3, which looks at y3 star and y3 hat. All right, so just so that this looks a little cleaner, we could say that, you know, the log probability that we're working with here is equivalently the log of some vector p of y. Right? We didn't actually have to write them all out. Okay, so what's interesting here is that now we can define L of 1, 2 and L of 3. So L of 1, 2, which takes in y1 star, y2 star, y1 hat, y2 hat, is defined as a loss of 100 if y1 equals y2, which equals purple, and that is not what y hat 1 and y hat 2 equal. So basically, the color purple here is extremely important. If these are both purple, and you're not predicting these two correct, you get a really high loss. Otherwise, we just back off to, say, Hamming loss on each of the variables, which would be an indicator function of y1 star not equaling y2 star, plus another indicator of, oops, sorry, y1 not, that's not right. y1 star not equaling y1 hat, plus y2 star not equaling y2 hat. And we get that otherwise. Okay, and then the last detail would be, we'll define L3 here to just be, again, Hamming loss, which is the indicator function of y3 star not equaling y hat 3. Okay. So loss augmented inference tells us to do the following. In the first step, we're going to define a new factor graph. And that new factor graph is going to have some log probability that we'll say is log p prime of x1, oops, sorry, y. So it's the log probability of some vector y, which is y1, y2, y3, and that's given by the log of psi prime 1, 2 of y1 and y2 plus the log, it's the same form as above, of psi prime 3 of y3 minus the log of z prime. So it's the same form as our original probability distribution, except that I've added primes to everything. And the key difference then is that now we have psi 1, 2 prime of y1, y2 defined as the sum of psi 1, 2, or sorry, yeah, psi 1, 2 with L1, 2. And here, we're assuming that you already know what y star is. So given the vector y star, we can define psi prime of 1, 2 by combining this loss with this factor. And then similarly, psi 3 prime is just the original psi 3 plus that loss L3. So once we've actually defined this new factor graph, now we get to the fun part. We can just run map inference on our new factor graph. So what is this doing? It's saying, well, we want the value of y, that is the argmax over possible y's, of the log probability of y under the distribution, not p, but this new p prime. And so running map inference in this way is significant. And we have that because of our carefully defined distribution, P star, y here is going to be equal to the argmax over y of the log of P of y plus the loss of y star with y. Oops. And this is the solution to the loss augmented inference problem. So essentially what we're accomplishing by combining these is we're saying that if we have a distribution and it factorizes according to some factor graph, and then we have some loss function and it factorizes according to the same factor graph, we can just add those two scoring functions together, and what we get back is an actual new factor graph, where if we run map inference on it, we'll be solving the problem that we set out to solve. Okay, there's actually a bug in what I wrote right up here. Does anybody see what I did wrong? Didn't even notice it as I was doing it. You're trying to maximize the log of this probability plus the loss.
Is log z prime constant, or does it affect, does it change depending on the example you see?
Good question. So here I was just writing this out as if it were an MRF. So we could do exactly the same thing where we just condition everything on an x, and the whole example would still hold. Just would have required a lot of x's. So that's okay. We can just assume that z prime here is defined as the normalizing constant for p prime. Yeah.
Should we be subtracting the loss?
Oh,
That's a score.
oh yes, actually. Okay, so there's two errors. Thank you. So the one that I was trying to fix here was, so we want to maximize the score and minimize the loss. So the first thing to fix here is this should be subtracted. The other detail that is just that what we're defining here is actually the log of these potential functions, right? So we're sort of saying that the log of the potential functions is being added to the actual loss, because it's really the log probability that is the sum of these individual log potentials, and the loss is a collection that is a sum of these little loss terms. So we want to work with the log potentials rather than the potentials there. Okay. So let's talk about convolutional neural nets. So in order to do this, so this is another topic like LSTMs, where I think a good portion of you may have actually seen CNNs before, but this is sort of so necessary. Like we need this to be. This is really central material to the course, so we do actually kind of want to carefully go through this. Okay, so the background here is really computer vision, sort of before deep learning took over. And so there, is this classic picture of how deep learning took over, which comes from the ImageNet contest. And it was a data set with 1.2 million labeled images and 1,000 classes arranged in a hierarchy. And the goal was, given a new image, you tried to label it with the correct class. So this is a picture of the actual hierarchy where I've selected images of birds. These are images of the German iris. These are images of courtyards. Okay. And the classic approaches to doing this were feature engineering, where people would build those functions that we've just been seeing, W transpose F. And that F function would be some really interesting and complicated function, like canny edge detection, which is taking the original image and giving us back a sort of filtered version of it that puts these really high values on pixels, like values of 1 on pixels that look like edges, and then really low values on things that don't look like edges, values of 0. Another example would be the Harris corner detection algorithm, which, given a picture like this, can highlight the corners with these little green dots, or up here it's highlighted the corners with red dots. And then there's other sort of more interesting and complex functions like sift features and hog features. And all of these got replaced when, in 2012, in this contest, the winner by a substantial stretch was a convolutional neural network that had taken as input the image and then passed through the image through a bunch of, 5 convolutional layers with max pooling layers interjected in between some of them, followed by some dense layers, followed by a softmax. Okay. And the output was this output of the 1,000-way softmax, which was a dense vector representing a probability distribution over the 1,000 different classes that we were trying to classify into. Okay, so we won't get to it today, but I'll eventually sort of give us some discussion of ResNet, which was sort of a much later iteration of this. So basically, what this picture is showing is kind of fascinating. So the architecture that we were just looking at came from Alex Krzyzewski, and corresponded to the LSVRC 2012 contest. That's showing its performance right here. So it had 8 layers deep and it got 16.4 error. The year before, the solutions had not used deep neural networks, so you couldn't really count them in terms of layers of depth, and the error was much higher. So this was a huge improvement in 2012. Then in 2013, someone came along and improved performance, though didn't really add that many layers. Then somebody else, doubled the number of layers and got another significant improvement. And then somebody else came along and added more layers, and the error went down again. And then these guys from MSRA came along and added a ton of layers and got a huge performance improvement yet again. So what we'll do is we'll actually kind of build up to what it was that went into this ResNet that actually successfully got them this incredibly low error on this task. And it's continued to get better past this point, but I think this was sort of one of the most significant jumps as well. This paper was cited like 30,000 times or something like that already because it introduced an idea that was just reusable all over the place. So this idea of residual connections has just shown up time and again, both in the field of computer vision and other fields as well that are using these sorts of deep nets. Okay, so first what we need to understand is that of convolution. And the whole idea of convolution is that so let me just take a step back here. When I say convolution here, I do not mean a convolutional neural network. I mean, convolution is just going to be some function that takes in some parameters and an image and returns another image, or maybe a set of images. So the idea here is that if you have an input image that's, say, 3 by 3, you can take a collection of a convolution, which is these parameters, 4 of them, 2 by 2, and you're going to get out an image where y11 is the dot product of this convolution with the upper left corner. And y12 is the dot product of this convolution with the upper right corner, and so on down the line. y21 is the bottom left corner, and y22 the bottom right corner. And so here, by dot product, what I really mean is an inner product of 2 matrices, right? Where you take you could imagine just taking that matrix and stretching it out into a vector, and then taking the dot product of those 2 vectors. Okay. So let's actually look at an example of this. So suppose that our input image is black and white, and so its pixel values are given by 0s and 1s, and then the convolution is also a collection of parameters that are 0, 1 valued. And so we could actually look then at the convolution just in terms of the actual sort of pictorial representation, right? All of the information of these 0s and 1s is encoded by which of these squares are shaded as blue. Those are the 0s and the rest are 1. So you could think of this convolution as basically being a level of transparency, right? The blue squares are opaque, you can't see through them, and the 1s are transparent. And so if we take that convolution and slide it along here, at each step along the way, at each different position, we're getting back an actual value for the convolved image. Okay. So, for example here, if we wanted to compute the value in the upper left corner, we could lay our convolution down over our image, and then taking its product is really just, because these are just 0s and 1s, adding up the numbers that we can actually see, right? Okay, so that's going to give us 3. And then this is going to be 1 times 0 plus 1 times 1 plus 1 times 1, which is 2. And then again, 1 times 0 times 1 plus 1, and so on down the line. So we keep taking these inner products. We get 3, 1, 2, 0, and so on to get the rest of the convolved image. Okay. So you could do a lot of different convolutions. So for example, here, I've chosen parameters that give us the identity convolution. So this is just going to make an exact copy of the image, where there's this annoying detail that we're actually going to lose the outer edge of pixels because our convolution operation is actually not going to be able to tell us what the convolution is unless we have a full collection of pixels to take the inner product with. We could also use parameters like this one, where we have 0.2 in the middle and then 0.1s around the outer edges, which will give us back a blurred version of the original image. And so that's actually what we're seeing here. And then you can actually, go online and find some little cute demos of different convolutions. So this convolution is a vertical edge filter, right? So it has 2 in the middle and -1s on each side, and it gives us back an image that's trying to kind of pick out the edges of these little vertical rice grains, right? You can do a different convolution which tries to sharpen the image. You could do a horizontal edge filter, and now you can see what we're getting back are sort of the pixels for most of the horizontal rice grains. And you can then do sort of other interesting combinations. This is not this is sort of a diagonal edge detector. This is another diagonal one. And so the whole idea is that, just these different convolution functions give us back interesting representations of the image. Okay, so suppose you were trying to define a linear model for image classification. One thing that you could do is you could just take all these different filters, like this, diagonal edge filter, this sharpened image, this horizontal edge filter, this vertical edge filter, and you could use each of those as a feature representation of the original image. And then you could build a linear model that just takes a dot product of those features with some weight parameters. Okay, so this is what people used to do in the early 2000s in computer vision. And they spent a lot of time trying to figure out how you could use these sorts of functions to good effect. Okay, so there's other tricks that you can play with convolution. Like one is actually downsampling. So here, what I have been doing so far is I've been using convolution with a stride of 1. That means that I move the convolution over 1 pixel at a time. But I could have used convolution with a stride of 2, which is where I'm going to shift the convolution 2 pixels at a time. So doing so is essentially now downsampling the image. And so as we go across here, we've just convolved the image, but now we get back from our original 6x6 image a 3x3 image. But you can see that it's actually preserved a lot of the information that was in the original one. Okay, so convolutional neural networks follow our usual recipe for neural networks, where we're going to have some training data, we'll choose a decision function, a loss function, and then train with stochastic gradient descent. But here, the actual decision function is going to be provided in part by this convolution operator. And some of the parameters are actually going to be the convolution itself. So this is a classic convolutional architecture from 1998, which was named Linnet after Jan LeCun. And the typical layers include things, at least, sorry, let me be careful here. The typical layers in 1998 included things like convolution, max pooling, fully connected layers, ReLU layers, and softmax. The typical layers in 2019 include basically all of these, except for max pooling. it's kind of gone out of favor, and we found that you can basically do everything that you want to do with convolution. Okay. So what the Linnet architecture was doing was following this key idea, which was we treat the actual convolution matrix as a bunch of parameters to be learned. And then we can have sort of some interesting layers interspersed that allow us to do downsampling. So we already saw one example. This is another example of downsampling by, say, averaging. Okay. So this is sort of the same example as we saw before. And max pooling was this idea that sort of replaced that, which was that instead of taking the average of all the values under the convolution, you could just take the max of all the values under the convolution. Okay. So this doesn't correspond to any particular assignment to values in a convolution matrix. So it sort of it requires its own name. So this really is a different function than a convolution function, but structurally it kind of behaves in the same way, where we slide this maxing layer over top to get back a max pooled image. Okay. So how could we train one of these? Well, with the convolutional neural network as a decision function, we then want to compute the actual gradient of one of these things. And so to do that, we rely on backpropagation. And so assuming you know how to implement backpropagation, the stochastic gradient descent training for the CNN is actually sort of the standard thing that we would expect to see. So here, we could say that our input is going to be some image x. Okay. And then we're going to have parameters at different layers, namely these alpha parameters from this convolutional layer. This is the beta parameters from this convolutional layer, and then some w parameters from this linear layer. Okay. And so our goal is to learn those three sets of parameters. And so the architecture here is sort of written out bottom to top, where we say first you apply a convolution layer to x using parameters alpha. That gives you z1. Then we apply a max pooling layer to z1 to get z2. Then we apply another convolutional layer with parameters beta to get z3. Then we pass that through a rectified linear unit, which we'll define in a second, and then a linear layer, a softmax, and finally a loss function to get back some score. So our parameters you could think of as just some object theta, which is maybe the sort of vectorized version of all of this alpha, beta, w, right? So you can imagine taking those parameters and stretching them out into a long vector, concatenating them together to get us back a long vector theta. And then we could initialize theta, and we could then just do stochastic gradient descent training where we sample one of our training examples, I, and then we compute the whole forward process, right? Which is going to first predict for us our distribution over outputs. It's called Fy. And then we'll have some loss function like cross entropy that looks at the predicted distribution and say the one hot representation of that distribution, which is the ground truth Y star. And then we run backpropagation to compute the gradient of this objective function. And then we just update our parameters with SGD. Okay. So the remaining question is just how do we actually do backprop? Well, for you guys, we're not going to ask you to implement this command. Instead, we'll just ask you to chain together a bunch of modules where somebody already figured out how to implement both the forward computation and the backward computation for each of those modules. Okay, so here's some of those modules. So this is a ReLU layer. So the input is a vector x of length k, and the output is a vector y of length k. And what we're doing is element-wise applying this function sigma to x. So where sigma of a is the max of 0 and a. So we've actually seen this function before in structured SVM, and we saw that it was subdifferentiable. And so we can actually compute a subderivative for it, which is just 1 if xi is greater than 0 and 0 otherwise. So you could use this partial derivative inside an adjoint computation to get back the partial derivative of the final output, dj, with respect to xi. And you would do that by assuming that the module receives dj dyi, and then you can compute via the chain rule the dj dxi's. Okay. So then for a softmax layer, again, we would have vectors of the same size as input and output, and we just exponentiate the inputs and divide by the sum of the exps. And then for backwards, the partial derivative that we care about is for each yi with respect to xj, and it works out to this lovely clean little form in terms of the y's, and again applying the chain rule where we actually correctly need to sum over the different values of yi, we can get back the partial derivatives. Okay, so there's this other little detail, which is you might need a fully connected layer with a tensor as input. And so you can actually imagine if your input was a three-dimensional tensor x, you could stretch that out into a long vector and then just apply a standard linear layer. And that would get you back something that you can work with. Okay, so the convolutional layer is sort of the last interesting one here, but honestly, when you look at it spelled out for this small example, you begin to see that the convolutional layer is not terribly interesting. All it is some linear function of the input and some parameters, or technically it's a bilinear function of the inputs and the parameters. And we can come up with different versions of it. So in the first case, we say, okay, we have one input channel and one output channel. Here, channel refers to what sort of computer vision people would talk about the fact that an image is represented not by just a single matrix of pixels, but rather a matrix of pixels for all the red values, for all the blue values, and all the green values, if you have an RGB representation of your image. And so those would be three different input channels. But you could also just have, say, multiple convolutions that are actually running in parallel, but have different parameters. And so if you have convolution number 1 and convolution number 2, then you're going to get output number 1 and output number 2. And if we take those outputs, those two matrices, and squish them together, then we get back a three-dimensional tensor. So the actual computation for the convolutional layer is honestly entirely uninteresting, right? You can figure out exactly what these summations actually mean, but at the end of the day, all we're doing is sort of some for loops over positions on the image, computing dot products of our convolutional parameters with the image itself. Okay? So if we write that out, we get something like these obnoxious looking summations, and then to compute the parameters, we get these obnoxious looking summations for the actual parameters. Okay. And the interesting bit is that if, in the more general case, you have an input which has, say, red, green, and blue input channels, then suddenly your convolutions need to be able to look at all of those channels at once. And so in 3 dimensions, convolution, the actual convolution looks at an entire block of pixels through all of the channels at once, going front all the way to the back. And then it slides that 3-dimensional block along just as we did for the 2-dimensional image. Okay. And so that's actually where we're getting this third summation, is the summation over Q and R here for the actual positions in the image, and the summation over C is for the channel. Okay, so a max pooling layer is just a max. And so just as with the ReLU layer, we can work with subderivatives here. We can work with subderivatives of a max pooling layer as well. And so we get a forward and a backward. Okay, so now we can double back to this Linnet architecture, which combines all of these different layer types into something interesting, right? So first, it does 6 separate convolutions on the 32 by 32 image to get back 6 separate 28 by 28 images. Then it does max pooling, which here is just called subsampling, to get back images of half the size, but still retaining the 6 channels. Then it does convolution again on all of these channels. So it does 16 convolutions to get back 16 slightly smaller images. It does max pooling again here to get 16 5 by 5 images. And then it does a fully connected layer a couple times until its final layer output. Okay, so here the AlexNet that won this 2012 competition was actually breaking up the computation for the image sort of into these 2 separate computations graph stacks that ran all the way up, and then it combined them together at the end. So what I want to do with the last couple minutes is talk about a third architecture, which is ResNet. And the key building block of ResNet that I want to highlight here is that of residual connections. Okay, so these slides are stolen from Kaiming's actual talk, and this was actually at CCD 15. So this was actually his presentation on this topic. And I kind of, it's maybe more slides, so I encourage you to go back and actually pick up these slides. I just kind of want to highlight a couple of the really interesting aspects of his talk in the minutes that we have here. So the first is that, okay, here's a depiction of AlexNet in terms of the layers that it was putting together, right? So it had convolution and pooling, and they were kind of, and then some fully connected layers at the end, and pretty large dimensions, you know, pretty deep 8 layers. And the models that followed it just kept getting deeper and deeper. So here, this is VGG. It had 19 layers, so now much deeper, but similar looking components. GoogleNet then had 22 layers. This was with the same year in 2014. And ResNet made all of these look kind of tiny with 152 layers. Okay, so this there was animation here is actually from his slides because he had animated this like zoomed sliding down through the 152 layers, right? And in some sense, exactly what's in here is not of great concern to us, except for the residual connections. And the residual connections are these little curvy arrows that you see kind of jumping along through multiple layers. And we'll look at what those are in just a second. So the first point of ResNet that they were making was that if you just take really, really deep plain convolutional nets, they actually have higher error as you go deeper. So here, lower is better, And so with a 20-layer net, you're getting this yellow line. 32-layer net, you're getting this blue, 44, this green, and 56, this red. So the 56-layer net is actually doing a lot worse than the 20-layer net. Okay. And sorry, here what I'm showing you is the actual test or validation performance. The dashed lines that are shown at the bottom are the train performance, and that's actually also pretty bad. So it's not even like the training performance of the deep net is doing better. So this was for CFAR 10, which is a data set where you're trying to classify 10 different classes. This was for ImageNet 1000, where you have 1,000 different output classes, and the same trend holds there. Okay, so the plain neural network is essentially saying we have some input x, and we have some output h of x. And there's going to be some weight layer, and some ReLU layer, and some weight layer, and then some ReLU layer. Okay, so it's some pair of stacked layers in this fashion. Okay. And the idea of the residual net is to add an extra connection into the network. And it's a really, really simple connection. So it's saying that, okay, we're going to take this x and we're going to do some complex linear ReLU layer to go through and get us back ff of xx. At the same time, we're going to define the output of this thing to be the sum of that complex function of x with the original value of x. So this is incredibly significant because if you are backpropagating through this function, the error is just going to backpropagate directly through that identity connection. Okay. Whatever error you were backpropagating to HH of XX is also going to backpropagate directly to XX. By contrast, if you didn't have that identity, your error is going to have to flow through ff of xx, and it might get shrunken or clipped or manipulated in some way such that you lose a lot of information about how you should be updating your parameter values. Okay, so this is sort of a residual mapping with respect to identity, and there are sort of more modern variants of this where you maybe take some weighted linear combination of these. But here, just this simple way of doing this identity works incredibly well. And they had this additional, very interesting insight, which is, so the usual way of kind of combining convolutional layers was to do, say, all 3x3 convolutions. Okay, so all of your convolutions are these little 3x3 matrices. And they said, well, let's try one other little tweak here, which is this sort of bottleneck trick, where they first have a convolution which is 1x1. Okay, so that's a funny convolution because it's essentially just doing some like direct linear combination of the pixels. There's no real convolution happening there. And then it does a 3x3 convolution followed by another 1x1. And when they say similar complexity here, what they mean is the time that it takes to do all of these matrix multiplications for this side is about the same as this. Okay, so their basic design is almost all 3x3 convolutions, which was really kind of an idea that came from this VGG model from 2014. And then they just made it incredibly deep with these residual connections and this bottleneck trick. Okay. And so what they're going to do is they're going to compare this plain net to this residual net. And what they find is that on the left here, we have the plain neural network trained on CFAR 10, and on the right, we have the ResNet trained on CFAR 10. Okay, so this is image classification. We have 10 different classes for the image. And again, for the plain net, deeper layers give us higher error, which is bad. But for the ResNet, as you add more and more layers, the error is going down. And this holds, again, both for and test performance. Okay, so here they're showing, you know, a 20 layers deep network, and down here, a 100 layers deep network that's doing better. Okay, so this was then their result on ImageNet, which has 1,000 classes, which is, you know, they did 152 layers and got this really low error compared to prior results. But then they went on and applied it to a bunch of other things. So they did object detection, where here object detection is where you're trying to, say, put a bounding box around, say, that refrigerator, that oven, that bottle, that knife, that bowl, that cup, the person that you can see his shoes in the very background there. It's hard to even capture in this light. So they were able to, with ResNet, substantially outperform the COCO detection results, which is this particular benchmark. Okay, so here's more object detection. And then they were also able to do instance segmentation, which is where they're trying to not just find individual, so they're actually trying to not just box the instances, but also find the individual pixels corresponding to those instances. So, so here what we're looking at is, you know, the yellow pixels inside here are a person, and these green pixels are also person pixels, but they're a different person. Okay? So this differs from the semantic segmentation task that you're going to do, where we would have just said all of these should be yellow pixels for person. Okay? So they're actually able to kind of separate out the instances of, you know, different persons and skis and backpacks in this image. Okay, so well, there's a bunch of visualizations. So anyway, the key kind of takeaways here are, you know, CNNs have revolutionized the way that we do computer vision. Residual connections are critically important, and we'll probably give you something kind of like a ResNet as sort of the baseline model that we'll be building a structured SVM on top of for homework 3. So it should be a lot of fun.